In this problem, we will consider the solution of this integral differential equation, where I have both an integral and a derivative in my equation for y. So to do this, we will note that the integral here is actually a convolution integral in disguise. Y prime of t is equal to 1 minus sine of t minus integral from 0 to t of f of t minus u times y of u du, where the function f is just simply the function, the identity function f of x equals x. So I'm just multiplying by 1 in here. Therefore, if I take the Laplace transform on both sides, we get s times y of s minus y of 0 equals Laplace transform of 1 is 1 over s. Laplace transform of sine of t is 1 over s squared plus 1. And then the Laplace transform of this convolution integral is going to be the product of the Laplace transforms. Laplace transform of the identity function is going to be 1 over s again, whereas the Laplace transform of y is y of s, pardon me. And so when I have this convolution, the Laplace transform is just going to be the product of the two Laplace transforms. So now we solve for y of s. We'll bring this y of s over to the left-hand side. We get s plus 1 over s times y of s equals 1 over s minus 1 over s squared plus 1. And then this is a minus 1 here. It brings the other side as plus 1. Okay, this fraction here is s squared plus 1 over s times y of s is equal to 1 over s minus 1 over s squared plus 1 plus 1. Then multiplying both sides by s over s squared plus 1, we get that y of s is equal to 1 over s squared plus 1 minus s over s squared plus 1 squared plus s over s squared plus 1. Okay, now the inverse Laplace transform of this is just simply sine t. That's a standard one. The Laplace transform of this is a standard one. It's cosine t. The inverse Laplace transform of this, however, is not standard. Now, there's actually a couple ways of getting the inverse Laplace transform of this, and I'd like to illustrate those. If I want to find the inverse Laplace transform of 1 over s squared plus 1 times 1 over s times s over s squared plus 1, that's what this is, after all, s over s squared plus 1 quantity squared. The inverse Laplace transform of this product is going to be the convolution of the two inverse Laplace transforms. So the inverse transform of this is sine, so let's make that sine u. And then the inverse transform of this is cosine, so cosine t minus u du. And I could have put t minus u and u here, and that would have been perfectly okay. From this point forward, I'll use the hint given in the problem that sine of alpha cosine beta is equal to the expansion that I see on the right-hand side. So equals integral from 0 to t of 1/2 the sine of the sum of the two angles. So if I add these two angles up, I get t plus 1/2 sine of the difference of the two, so u minus t minus u du. So integral from 0 to t of 1/2 sine t plus 1/2 sine of 2u minus t du. Okay, so from this point forward, we need to take the integral. The integral of this with respect to u is going to be 1/2 u sine t. The integral of this with respect to u is going to be negative 1/4 of cosine 2u minus t, where I'm evaluating from t to 0. If I plug in t equals u equals t, I get 1/2 t sine t minus 1/4 of cosine 2t minus t is cosine t. If I plug in 0 for u, I get 0 there. If I plug in 0 here, I get minus 1/4 cosine of negative t. Okay, so let's see what happens here. Cosine of negative t is the same as plus cosine t. So I have two minuses. That's positive. That actually cancels perfectly this minus. And so I end up with 1/2 t sine t. And so that's the inverse Laplace transform of this product. And so coming back up here, we get that y of t is therefore equal to sine t. This part is cosine t. And then we just found that the inverse Laplace transform of this is going to give us negative 1/2 t sine t. And so that is the answer. Okay, now I alluded that there is an alternate way to figure out the inverse Laplace transform of this, and it's as follows. If I take the derivative of 1 over s squared plus 1, that's equal to negative 2s over s squared plus 1 squared. So it's going to be, this is s squared plus 1 to the negative 1. That's going to be negative s squared plus 1 to the negative 2 times the derivative inside, which is 2s. Now that's basically what I want, except for the minus 1/2. And so that implies that the derivative of negative 1/2 times 1 over s squared plus 1 is equal to s over s squared plus 1 squared. And therefore, the inverse Laplace transform of this is going to be equal to the inverse Laplace transform of this, negative 1/2 sine t, times an extra negative t by my rule for taking the inverse Laplace transforms of derivatives. And when the minus signs cancel, I get exactly the same thing that I had before. So anyway, that's an alternative way of figuring out the inverse Laplace transform of s over s squared plus 1 quantity squared.